Hello, Luke.
Hi, Sujesh.
Hey, thanks.
Pretty good.
No one there yet?
I see.
It's early morning, 9 o'clock. It's hard, I guess. Are you taking any other courses other than the courses you're taking with me?
No, I have 2 credits of 575, but that's
Good.
yeah,
Yeah, that gives you more time to do research with
right.
whatever you want to do. Yeah, that's good. Oh, I did see your homework. You use LaTeX to type your homeworks. That's not very usual.
I kind of had some practice last semester because I didn't have easy access to a scanner.
Got it.
So
I see.
I figured it was a good time to learn.
Yeah, it's surely good to learn, but when it comes to diagrams and all that, it becomes way too hard. Yeah.
Right.
Is that the reason why you're typing your homework? Because you don't have a scanner with you?
No. So I've used some scanner apps on my phone, but I don't really like using the scanner.
Okay.
So I've just also been trying to learn LaTeX.
Good. Yeah. You're surely doing a good job on that. Yeah. This is good. Michael?
Yes. How are you guys doing?
Good.
Good.
So it seems like today is a day where everyone is going to be online.
Oh, yeah.
One should map the weather and how gloomy it is outside with the online attendance. There must be a correlation.
Yeah, no, I woke up and looked outside and I was like, I don't want to get out of here.
Yeah. Some of the advantages of online, very few advantages, I suppose.
Yeah.
Yeah, I don't know what's happening with others. So, since we are at least 3 of us, maybe begin. Moses did say that he may not be there. So let's make it 4 of us. So I think Aliyah and Khalida. Okay. So, I think that will be the first time I'll be teaching, or at least this semester, with no one in the classroom. So this is all online, yeah. Okay. We have, so there was a homework due today, I see. I haven't checked the homework itself, or the submissions itself, but I assume it's limited. And homework 3. September. I haven't posted this yet because I want to decide whether I want to use the spherical or the cylindrical, most probably cylindrical, to do some calculations on that. So will be posted.
Okay, good job, Basil, raising your hand. Go ahead and tell me how many.
Will be posted in a day, I suppose. So that's all. And it is due on next Tuesday. Okay. And there's midterm, so that's homework 3 that's due on Tuesday, and we will have a midterm 1, which is due, which is, and I'll see, but maybe whatever I build on this, maybe I'll distribute it into midterm and homework. If that is the case, then there might be a part of midterm that will be a take-home part of it. Okay. Okay, so that's something, and let's we want to do a little more on the metrics part. I want to do some properties of the metric, whatever we constructed out there, and then talk about what is called a connection and then the curvature. So that's the idea. So we are doing curvilinear coordinates. Hopefully we'll do one more lecture. Because this can go actually very long, but we are cut short on somewhere. Is that too light? I think it is too light.
It's pretty light.
Yeah.
Let me change that. So probably this will be better. Yeah, very
Oh,
good.
yeah.
Curvilinear coordinates. We're talking in terms of 3 or 2 sets of coordinates. One is xi, which is a short form for x1, x2, x3. In principle, any set of coordinates, and there is another set ui, which is u1, u2, u3. Think of this as spherical polar coordinates or cylindrical polar coordinates. Cylindrical is much more easier, at least in this part of the calculations when it comes to differential equation level. Cylindrical coordinates doesn't have sufficient symmetry that it can usually solve problems, or spherical symmetry is much more symmetric than cylindrical, so it is nicer in that sense. But at this stage, often cylindrical coordinates, because it is 2 dimensions, it's easier to deal with. So that's your 2 coordinate systems. And the first thing you can do is define what is called covariant vectors, right? Covariant basis vectors, that's what we did. And this was EI equal to change in the position vector R, and R is a geometric object that should be thought of as a geometric object independent of the coordinate system. In our coordinate system, it has the same meaning, and that's what I mean by it is a geometric object. Right. So this is UI. Immediately, a closely connected idea is that of a line element. That is dr is equal to how much you move, right? So it's dui times dr, which is nothing but dui times. So when you think of it as components, this surely has a very good interpretation. But this is nothing but this, and this is nothing but the partial derivative, the chain rule and partial derivative. So in that sense, it's a clear idea there. We have what is called scale factors. Again, while we are in covariant cases, define the scale factor as hi is the magnitude of these vectors, or the basis vectors, is called the scale factor. So that's a summary there for covariant basis. Right afterwards, we can define a very contravariant basis, which is defined using the normal vectors. Remember that xi and ui are coordinate systems, so that it's a family of surfaces in that sense. And we define this to be I equal to gradient. Immediately one leads to the idea of orthogonality by construction. These are orthogonal in the sense that I dotted with EJ. That means to say that pick one of the basis vectors from the contravariant basis and pick the other one from covariant basis, and you take a dot product between them. So there are two kinds of dot product here. So purposefully it is written in a mixed language. There is a vector sign as an index there, and there is an I. So in principle, each of these basis vectors is a vector. That means there are 3 components, and there are 3 of them. So there are 9 components in that sense. So these are 9 components here, 9 components there. But then you contract, then so you lose 3 from each of them. So you're left out with again 9 components. This is equal to delta ij, but how do you see that? Let's look at it from the definition itself. Gradient means it is du I over dr. So this is nothing but du I. That's another way of writing that. And you're dotting it with a covariant, which is dr by duj. Again, use the idea of chain rule. This time, these two can cancel out. Right? So the cancellation doesn't really work like the way we usually do it. It is a partial cancellation, but the idea is that they disappear, and then we have I by duj, and that is by definition, right? These are family of surfaces. If you're on one surface, you don't expect it to change with respect to another surface. Otherwise, you won't be having a unique representation of the coordinates. So that by construction again is delta ij. That's your orthogonality. And once we reached here, we defined what is called, or we introduced the idea of metric. And for that purpose, we said that let's define a distance as dr dotted with dr, two line elements coming together that will be defined to be the square of the distance between two infinitely close points. And if that is the distance, then substitute this definition of the line element there. So this is the ui times I dotted with uj times uj. Again, we are using a vector for one of the indices, and the dot product whenever I write is between the vectors. And we rewrote this as dui j, and whatever is left out is defined to be gij. That's the components of the metric, if you want. Metric in the sense that how much do you want to multiply with each component, if you want dui along each direction. Right. So gij in this sense was recognized to be the dot product of the covariant basis vectors, and we explicitly evaluated this for some of the coordinates, like cylindrical coordinates. We did this in the class. Spherical coordinates was a simple extension, and in your homework you did this even for a non-orthogonal system. So you have a reasonable idea of what this means. So now let's extend this. First thing is we want to talk about what is completeness relation. Right. Notice when you bring in two basis vectors together, you can either dot them by the vectors in between. So, for example, ei dotted with ej. Right. This is orthogonality, right? When the dot products are multiplying each other. So orthogonality. Or orthogonality. If you want a comparison with what you've already seen in quantum mechanics has some special properties that you're working with Hermitian bases or Hermitian operators, and this will be equivalent to, we will have j here and I here. So that's how you will see this in quantum mechanics. So I'm sure you've seen this notation. That if you're not seeing it, just ignore it. Whenever you see it in the future, just give it a keep in mind that there is some connection here. But there is another relation you talk about in quantum mechanics, and that's this, right? The outer product. I times j, and that has to do, or actually, I don't want to write j, I want to write I. And in fact, there's a summation sign because in quantum mechanics, you don't assume this index relation. That's I. Actually, I don't know how to wear the mask, right? There's no one here. Okay, so that's the completeness relation, and the analog here is going to be that this is EI, but notice there is no dot product now. So earlier, so if you write two sets of basis vectors here, earlier what we did was take the dot product there between the two indices, the vector sites. But in this case, we will take the dot product with respect to the index and leave this open. Leave the vector signs open. And that we want to figure out what this is equal to. That's what we want to know. And it'll come out.
You said a dot product between the indices when it's like that?
Example, okay, so what I mean here is that EI, when I say EI, right, this vector which has this arrow on it, that is also an index in principle. This is, if you want in pure index notation, this is the 3 components of the vector and ith component of each, correct? Is that clear what I mean? So what this means is that the first eigenvector, second eigenvector, third eigenvector.
Okay.
So these are the 3 components of the first eigenvector, right? These are the 3 components of the second eigenvector. These are the 3 components of the third eigenvector, right? So there are total 9 components in that.
Okay.
Whenever we talk about 3 unit vectors, there are 9 components. So they basically form a what do you call it? A tensor of rank 2. And here, in orthogonality, what we have done is that we have dotted the 2 vectors in the sense that when I say vectors, I mean the arrow vectors, that's being dotted. But I also have the room that I can actually dot it with the index. I can say it's an outer product in that sense. So this is outer product here. But I'm summing over. I think the best way to say it is that that's summing over. So what this means is that this is E1 plus E2 plus E3. So that's precise, right? So probably when I'm making it a simplistic language, I'm losing the accuracy in that statement. Is that clear? Any confusions there?
Yeah, that makes sense. Yeah, it's a little confusing when you say you're just dotting the.
Yeah, so it's not really dotted. It's an outer product here. So wrong statement. Yeah. Like dotting in the sense that when you think of it as an index, whenever index comes together, that's a dot, right? So in that sense, it's a contraction if you want. Right? But keep it as an outer product. That's the best. Okay. So we would like to know what that is, and so this is EI, the contravariant times the covariant. Let's explicitly write this down. So that's gradient of UI and times partial derivative of the position vector with respect to the coordinate UI. And that's the same as partial derivative of the coordinate UI, R and R times UI. Notice there are no dot products here, so whatever is this vector and whatever is other vector, the 2 independent vectors, so it's a dyadic in that sense. But the I is summed over. So we can use the idea of partial derivatives, right? Partial derivatives again, chain rule. So we are almost saying that the derivative of the position vector with respect to the position vector itself, right? That's what we are talking about. So if we use idea of partial derivatives, chain rule, so that goes away, and we have by R of R, right? So. But notice those are 2 different vectors, so there is no dot product there, there is no cross product there. If we get this back in the gradient form, this is gradient of the position vector. But in whatever coordinates you write, this will always come out to be equal to 1. Like the identity in that coordinate system, right? UI, or yeah, whatever this is. So we will write that as the unit vector. Okay, so for example, this is in one coordinate it is this. If you were to work in rectangular coordinates, this is just x1 plus x2 plus x3 with the idea that this is I, right? So this is I hat plus j hat plus k hat. Again, think of it in this form. If you're familiar with quantum mechanics, you would say if there are n basis vectors, you put them all together, right? So each one of this is a matrix. In a sense, it's a projection vector, projection matrix. It projects the operator in that particular direction, right? This is, if it is one, at least this part of this one will project, will find the component of the vector in the I direction. So same idea. Here, each piece is a projection operator. Okay. So that's one, and that is also one more information you can immediately build. Once you have this, you also can take a dot product inside between those two vectors also. So that's it. You can kill the outer product by taking a dot instead in there, and that will be the trace of one, and that actually gives you the dimensionality of the space. This will always be one, and that will give you the dimensions of the space. It's called the dimensionality, right? I think dimensionality. Right? It's called the dimensionality, I suppose, or is there any other technical word for that?
Not that I know of.
Yeah, I think so. For example, a three-dimensional space, it means it's three. Two-dimensional, it's two. And even if it is a good question as to will this go through in Minkowski, it will go through in Minkowski also. But I haven't. I usually don't work in this language there. So yeah, so maybe an extra credit if it is possible at all, because you'll have to work out all the coordinates. At least you can think about it. You don't have to calculate everything. So extra credit. Because there is a negative sign in the Minkowski space, will this work for? Will this be true for Gij being equal to +1, +1, +1, -1? Like I think I talked about that notation earlier. This means it's a diagonal matrix with three of them diagonal +1, and the other one is negative. Again, just barely think, give it a small attempt. If you're not familiar about it, don't go ahead and calculate. You're welcome to do that, but I'm not asking you guys to do that. So do it at your own curiosity. I think it will go through. Okay, so that's completeness relation. So every time we have any one of these basis vectors coming in, we have the choice of multiplying it with either using the orthogonality or the completeness relation, exactly like we work in quantum mechanics, right? Whenever we have a relation, we try to use the idea of completeness or the orthogonality to get various relations. So let's see how this works. So we have, suppose we are interested in a vector, right? So this is a vector. Again, when I don't write it in terms of any components, that's a geometric object. By geometric object, I mean it has a meaning irrespective of any coordinates that you think of. Like there is a space, and think of an actual arrow there, and that's what that vector means. Multiply it with a dotted with 1, and we immediately have this is a me write this here, A dotted with, let me first write it in terms of rectangular coordinates. So this is xi, xi. Remember, 1 in rectangular coordinates is x hat I, with I being summed over. My notation here is that x hat I is, or let me write it explicitly, x hat 1 is I hat, x hat 2 is j hat, x hat 3 is k hat. Right, I think we introduced this sometime in the last class. So that's the notation. So that's this, and this we will define it to be AI. So this is AI times X I hat. So this is AI. So the components in the basis of covariant vectors are upstairs, in the sense they are covariant components in the basis vectors of, contravariant components when you look at the index of the components, but the basis vectors are covariant in that sense. I could have also multiplied this on the left hand side, right? So let me write this here. This is AI X. I could have also multiplied it from the left. And that's xi hat dotted with A now. And this I will define it to be a subscript I, and that gives you another set of component, and that is right. I could have done the same idea again in slightly different form. This is A dotted with, let me first define those quantities there. So what I have here is that a vector A is equal to AI times xi hat, and these are components, so contravariant components. Of A, of the vector A. Same thing, vector A, I could write that as x hat times, this is covariant components. And notice how if the basis is contra, the components is covariant, and sort of straightforward. That falls in there. That's good. Now let's, I didn't have to work with rectangular, right? I could have immediately done the same idea with 1, and that's equal to A dotted with, this time, another coordinate system. Again, 1 being multiplied. This time, these are the components of the vector in the basis of another coordinate system. So they need not be the same components as that. So I call them a bar. Make it very small so that there's a small confusion, especially when I'm using the blackboard. That's a vector sign, and this is just a bar. So this is a I, and this gives you a bar I I. Okay, so be careful with, especially if you're handwriting it, be careful to differentiate with between the arrows and the bars. If you're in typography, usually you write the vectors with bold signs, so that will be, and that's less confusing. There are no bars there. Do the same thing in here with the opposite multiplication or dot product. So that's equal to I dotted with a vector A, and define, oops, that's on the other side. This is, define this to be the covariant components, and we have I times a bar I. And all these four quantities are the same because it's the same vector, correct? So, principle, I have four relations if you want. So that's a vector A, geometric object, and that's equal to x sub hat I AI. That's equal to AI times AI times x hat I is also equal to a bar of I times E bar I, and that's the same as I times a bar. And all these are identical. Let's pick one of them from the extreme left equality, or not extreme left, the second equality from the left, and let's again play around with it. That's the easiest because it's rectangular coordinates. So this is xi, and that's ai times x hat. And we would like to know how are these covariant and contravariant components related, correct? That's what you might be interested in. And these are two vectors, so both are vectors, but remember this is what you do in Fourier transformation also, or for that matter, any function space or any vector space in principle. And if you want to get one of the components, multiply it from the left or to the right. For example, if I'm interested in the ith component, I just have to use orthogonality here, correct? So let's do orthogonality now. So I multiply it both sides with x hat. I is being already used up, so I have to use j. So j dotted with x hat I, and I have to do the same thing on the right hand side, right? So this is x hat j dotted with ai x hat I. Notice this dot is between the vectors. These are components for each I. These are just numbers. And did I do this? Yeah, that's correct. Okay. So that's this uses orthogonality relation. So that's delta ij, but then there is summation over I that makes it a j. And that's equal to ai times, I can either move x hat this way or that way. Let me move it to the left. So this is xj dotted with x hat I, and then there is ai. So these are two covariant eigenvectors coming together, and that's your metric, right? But that's the metric in rectangular coordinates. Rectangular coordinates has a trivial metric. So this is the rectangular coordinates. This is just delta Ji. Notice this is metric, right? So this is a metric. We'll do this again in the other curvilinear coordinates. It will be much more clear.
Isn't the metric G?
It is G, but okay.
Isn't that the delta J? Oh, okay. I see what you did. I got you.
Right?
It's not. I was thinking you put the J up top.
No, J on the bottom. Yeah. So in rectangular coordinates, the metric is nothing but the Kronecker delta itself with both indices down. That's a very special case. Correct?
Yeah, that makes sense.
Do the same thing that if this is such a trivial example that this can lead to confusions, let's take the curvilinear coordinates, right? Again, write down on the extreme right equality. We get the components again. So this is a bar I. I is equal to I times a bar I. So the contravariant components, covariant component, and multiplying it with the eigenvalues. Again, do the same idea. I want a connection, so I will use orthogonality, right? In this case, I want to get rid of this, so let me multiply it from the right hand side. This is a bar, not a vector, a bar I. And this is I times, I want to take it orthogonality now, so this is dotted with J. So whatever I do on the left, I have to do it on the right also. So it's bar I. J, and that is done. Correct. Again, if we move this around, again we should be careful when that is possible and when that is not. If these components were by any chance not commuting with that, then we should be careful. But here, since we are doing this as a first example, let's not worry about it. And if we do this, this is E bar I, and dotted with E bar J.
So I have a quick question. How exactly do we know when we can commute and when it's a like whenever the relation is a commutator relation? Besides just saying like, hey, in quantum mechanics, when you deal with waves and probability, it doesn't commute, it's a commutator. Like, what's the key indicator here?
Key quantity here is that if you have two quantities A and B, right? Hopefully you have an explicit idea of what it is. Currently these are abstract objects, but I didn't tell you what A is, right? So you have to check by commutation. I really mean AB minus BA, is it 0 or not? If it's 0, it's commuting. When does it not happen? So instead of telling you that, so this is a definition. So this is commuting, this commutes. That means AB is equal to BA. This is not equal to 0 means does not commute, right? I have not said anything different. Probably you already know this, right? So that's a definition here. But instead, what I have been trying to tell you is that if A and B are matrices, right? If A and B are matrices, there's a very good chance that they won't commute or does not commute. Okay? And that's what I mean by unless you're in quantum mechanics, because in quantum mechanics, you typically deal with matrices.
And do dyadics always commute?
No, dyadics also are matrices. They don't.
Okay.
They don't.
So okay.
Yeah, they don't. Unless again in quantum mechanics, there are quantities that commute. Right? Those are the, for example, energy and angular momentum might commute if there is spherical symmetry. Right? The Hamiltonian and something will commute. So then it becomes nice quantities. Like those are the measurable quantities in quantum mechanics. So though leaving that interpretations aside, if your matrices, just from mathematics that we know, they don't commute. So if these components of this vector were matrices, you have to be careful.
Okay.
Second place where that doesn't happen is your differential operator and the function, right? If A was equal to gradient operator and B was, so let's say this was equal, or this represents that, and B was equal to electric field, let's say, or this function F, then again, it is different to say that gradient of F is not the same as F times the gradient. Right? These two are not the same entities.
Yeah.
Again, this shows up in quantum mechanics also in some form, momentum and position. So they're very closely related. That's the reason why, in a sense, you can say very naively speaking, why you see in electrodynamics you have a wave and particle duality, which is very much connected with the quantum mechanical interpretation because you have these operators showing up. So.
So when you get into like the when you extend electrodynamics using like quantum ideas or special relativity, then does it become, are you thinking about things more in terms of matrices again?
That's correct. That's correct. Yeah, that's correct.
Okay.
Yeah. That's exactly what happens. The only difference is that even in quantum mechanics, these are all infinite dimensional matrices. Right? That's the non-triviality there. The trace of the matrix is not very well defined. I think the very angular momentum probably is the only case where there are finite. No, there are finite cases, but often the usual physical quantities like energy, momentum, and they're all infinite dimensional. So that's a non-trivial.
Okay.
Like again, so for example, so this is an extra credit, right? Just completely off the. So we have momentum. Yeah, so think of one-dimensional Heisenberg uncertainty relation, x, comma p is equal to IH bar, right? It's one-dimensional completely. So this means that x, comma, there are two quantities, physical quantities, which relates, which can be written in this form. And you immediately say that, oh, x and p cannot be numbers. Correct? That's an immediate conclusion there, because if they were numbers, they will subtract out there is 0 on left hand side, that is right hand side, they are not numbers. So then you say that, okay, maybe they're not numbers. Another thing we know that does this job is matrices, right? So x and p are matrices. And there are position matrix representations of position and momentum. And then the question is, the extra credit question is, come up with one representation of x and p, the many. Construct one such matrix for x and p, which satisfies this relation. Right? Remember, so we want to build a matrix x and p, which when commute, you actually give you 1.
Okay.
My phone just got switched on and it was playing something weird. Okay, is that question clear?
Yes.
And maybe it's not a very trivial, if you go logically, you get stuck very quickly. So there's a small hint I can give you. Hint, right? Or a contradiction to, you can stop, like you can say that, oh, I don't want to work on this because of the following point. If I were to take the trace of this equation, right, trace distributes, so trace of xp, right? Now these are matrices, remember. Trace of xp minus of trace of px is equal to IH bar times trace of 1. Right? That's identity matrix on the right hand side. Now, trace of a matrix AB and trace of matrix BA is the same. That's just a matrix property. So this is equal to 0 on the left hand side, but the right hand side is not 0, right? Because this is a dimensionality. So you say that, oh, I will never be able to build a matrix to begin. Right? So you stop working on it right there. But I still hold the question that no, you have to find the matrix.
Okay.
Okay? So that is the solution. So look up and think about it. I kind of gave it away in the beginning statements right before I was stating the question. So infinity is the hint, right? Like, these kind of relations you can get away with when you're working with infinite dimensional quantities. So that's the key, that look for infinite dimensional matrix. Finite dimensional matrix cannot exist just because of this. Impossible. So you have to go to infinite dimensional, and there you can get away with that relation. Okay.
I can't remember the physicist's name, but he's one of the popular physicists in the world, and he said, it feels like when we get answers at an infinity, that it's the universe telling us that we have no idea what we're doing.
I would say no idea is going too far, I guess. Yeah, good. No comments. How about that? Okay. I think we have pointed this out a few times. Yeah. Okay. Yeah, so that answers, I hope, clarifies the question that whenever I say quantum mechanics or electrodynamics, both have that feature of non-commuting objects, but in slightly different ways, or maybe very different ways, but sort of gives you the same physics. And the beautiful part is that there is physics associated with the purely commuting on the non-commuting part, and that becomes new physics in that context. Anything that has an H bar in it, that is a non-commuting object, and that's new. That is new in the sense in classical mechanics you won't be able to have that. Right. So that's a remarkable part of that, non-trivial part. Okay. So we have this down here, right? So we have this construction in there, right? So what we can say is that this is delta ij for sure. So, and that goes with I and gives you j. So I have bar j now, that's equal to, what is this equal to? I haven't really defined this, right? Because when we define the metric, both were downstairs. So we can always define a new quantity. This will be ij, and actually this shows up in your homework, I suppose, right? Which you submitted today. Gij. I think it's better to write it the other way. So nothing significant, but I, G, I, R, J. Where I've used the notation that Ij is equal to I dotted with J. So it seems like the metric does the job of switching the covariant to contravariant indices. Think of this as matrix. This is a matrix. Multiplying a vector gives you a vector, right? That's the way to interpret that. And it seems like the metric does that job. Let me do the opposite. If I were to, let's again begin from the same first equation.
Really quick, is that a vector I on the right hand side? A, you have A bar J, and then that's equal to A.
Bar, just bar.
Okay.
So almost every A on this board means this part of the board is bars, no vectors.
Okay.
So again, let me start over. Get the opposite relation. This is I is equal to vector I bar I. And this time, let me multiply with E j dotted with I. Okay, that way I use the orthogonality on the left, but I will do the same thing on the right. I'll commute it right away because we talked about it just now. And this is E j dotted with EI. This is orthogonality. That gives me a delta ij, Kronecker delta, and that makes this a bar j. On the left hand side, I have a metric, the original metric. And this is so let me write this as G J I times A bar. So it seems like what's the two relations? So here, if I want to go from covariant to contravariant, I use the metric with the indices in the superscript. And when I want to go from the contravariant to covariant, I use the metric with the subscript. And it is clear, notice the way I sets, you know that what you want to do. It's with a little practice, that's what you will always do. In fact, at a user level, once you are doing, for example, in particle physics or in relativistic physics, this comes in every step. Then this is the two quantities that is the most basic entities. These are all concepts that lead to that, but at a user level, this is all you use. It's pretty much like the index notations. We can build it in a certain form, but eventually it is just there are two things, right? Either you contract or you use the the Levi-Civita symbol. That is also, once you do this, there is also this chain rule, right? So let's do this. So let's start from AJ. So let me start from let me write it as A bar I. There's a case so that I exactly use this. So this is G J I times a bar I. That's rewriting that same statement again. But now use the earlier equation to replace the contravariant with covariant again. So you're making a loop out of it. So this is G J I. A bar I, now I have to be careful because I have I here, but if this relation is for J, I cannot recycle the indices, so I have to come up with new indices. So this is the same as this was a bar, this was I, so let me call that K. This is K, G, K, and it was I to begin with, so I write it as I. And that leads to the idea that, but these are the same covariant quantities. So whatever is the product of these two metrics has to be a Kronecker delta. Right? This must be. Right? So this must be. That suggests, right? So this must be G J I times G K I times A bar K. This must be a Kronecker delta. So this implies for consistency, we should have G I times G K has to be equal to delta J K. Necessarily true because they should satisfy that. And there are other properties you can build from here. These are symmetric objects, so you can rewrite it and write it as inverse of each other. So one quantity is the inverse of the other. So the metric will always be the inverse of, or the metric in the covariant basis will be the inverse of the metric in the contravariant basis.
So are you allowed to swap indices on a metric? So can you do G, I, J, G?
Yes. Not in general, not always, but it turns out that the metric, actually we might be able to look at the, so this is the metric, right? You can ask, what is GJI? GJI will be equal to E bar J dotted with E bar I. All right. And what did I do? Yeah. So 1, 2, and 2, 1. It's not very obvious, right? That should be actually symmetric. As far as I know, it always comes out to be symmetric. Okay, so how do you see that is symmetric? So it is. So your question is, are these two the same? Yes, they come out to be a symmetric matrix. Okay, but how do you see that? So, for example, one of the cases could be E1 dotted with E2. Yeah, because these are two vectors, right? These are dot products of two vectors. Yeah, exactly. It doesn't matter whether you're doing this or this. Right? In standard coordinate systems, think of cylindrical coordinates. E1 is rho hat, right? And this is phi hat times rho. So it doesn't matter whether I multiply it from this side or that side. So this is the same as rho phi hat dotted with rho hat. Is that clear what I meant?
Yes. So it would be okay on the bottom to write, Gij, Gjk is equal to delta I.
Exactly. Then that has that matrix immediately. And exactly, that's correct. So A metric is a symmetric sort of by construction.
I have a related question.
Yes, yes.
So on the left-hand side of the board, when we're first expanding, yeah, exactly. So I noticed that you're very careful to leave, like, when you're expressing the unit dyadic, you use like E upper I, E lower I, and it seems like it should come out the same if you use E lower I, E upper I. So I was surprised when you like multiplied E upper I, E lower I on the left instead of just switching, like, does that make sense?
Yes.
Yeah, so.
Notice that this is a completeness relation.
Mm-hmm.
Completeness relation matters where you keep it. Orthogonality doesn't matter. This is orthogonality. Right? And this is completeness. So in that sense, it is different slightly. So yes, you're correct that I've been careful. So usually the idea is to try to keep it. It doesn't really matter, but try to keep the eyes adjacent to each other. They will always come one top and one bottom. Tries to keep it adjacent, but you'll be limited. Like you won't be able to keep it adjacent. That's the way to put it. Like very quickly, we're going to do connections and curvatures. There'll be too many summations and too many things. You won't be able to keep it all together. Ideally speaking, you would like to. Then why do you want to keep it? Because then it has this matrix multiplication idea. Right? If this is a matrix, so for example, if I have a matrix Mij times xj, then I can think of this as a vector and this is a matrix and column multiplying it. The summation is over the column and the row. So you have this matrix multiplication inbuilt. That's the only motivation for writing it in that form.
I see.
As a beginner, you can put it wherever you want. It's just for like with some experience, you realize that, it's good to keep it like that. So you try to keep it. That's all.
Okay.
Pretty much like, doing dimensional analysis. It's not necessary to check dimensions in every equation, but with some practice, you get so much stuck up with it that you always check your dimension in every step in your head. So that's something like that. It's not necessary, but useful.
And then I have one more question about the last step with the two metrics. Mm-hmm. If you were to switch the positions of the G's because of the symmetry, it's still the same. So if you did the contravariant first and then the covariant second, it's still
okay.
Okay.
But metric is very special in that sense. Metric is very special, has a lot of symmetry in it. Only that you can do. A general tensor, you cannot do that.
Okay.
Right. For example, if I have some arbitrary tensor Tij is not equal to Tji, right? So where it sits matters. Right? But metric is very special. It's symmetric and it has this inverse property. A lot of things it does for you. In fact, this is often one of the starting points. Like you can almost, given the metric, you can build everything in the reverse. That's also a theme you can use. Like what I did is that I gave you the coordinates and went and built the constructed the metric. But you can say that I only know the metric, and then you can rebuild the coordinate system to a certain extent, or all the important quantities can be rebuilt out of it. So that's another theme which you can use. Any other comments? Questions? Okay, so one more thing. 10 more minutes. In the same spirit. So there was 2 equal, so maybe I should write that down again. So there's A is equal to, let me so there was x hat I, AI is equal to I, x hat I is equal to, let's say, a bar I EI, and that's equal to E. Right. That's an equality. We did the second equality, fourth equality. That is also the second equality, sorry, third equality sitting there. Maybe we can get some information from that also. So let's do the same idea there. Right? X hat I is equal to right, and let's do the same idea. Multiply it with use orthogonality on one side. Correct. Now here, notice there is a difference. Here we are mixing up components. The left hand side is the components in rectangular coordinates. Right hand side is components in curvilinear coordinates. These are mixing up two coordinate systems. So again, do the same trick. X I at dotted with let's say EJ. And that's equal to a bar I multiplied with that. I use the orthogonality and immediately say this is EJ. So I can write my a bar J is equal to AI times, let me write this as not T, let's say R, or transform S, R, let's say, R. Where Rij is a short form. This is a transformation matrix actually. So T is the, yeah, let's put T. T is the right letter for that. T. So it's a transformation matrix connecting the components in the rectangular coordinates with the curvilinear. But what is Tij? Is equal to Xi hat dotted with E bar J. That's the same as X hat I dotted with, this is contravariant, so it's gradient operator, right? Gradient operator of UI, right? But these are the components of the gradient operator in the rectangular basis. So that's nothing but d by dxi of UI. Sorry, UI? No, hold on, mistake. This is uj. Copied it wrong. That's j. So the transformation matrix, this makes sense. Like if you think about it for a moment, stare at this, it makes sense. The transformation matrix to go from one coordinate to the other is the derivative of each one of those family of surfaces coordinates with respect to the three coordinates in the rectangular coordinates, partial derivative of that. So that's your transformation matrix. That's what this is, right? So that's your T I J. Right? Similarly, you can get the opposite, right? I can get the conversion from curvilinear coordinates to the other one. I just have to multiply the other quantity. So let's put that as extra credit. Right? Derive a I in terms of a bar J, right? And let's say it will be D inverse. Let's call it S. Right? Find S. Right? But having said that, now this becomes in some language at some level of building up this theory. This becomes the definition of a tensor of rank 1. This is a vector, right? Transformation of a vector. So this is a transformation of a vector, right? From one coordinate to the other coordinate, and vector, remember, is tensor of rank 1. tensor of rank 1. And then you immediately build, oh, if I know the tensor of rank 1, I just have to generalize this to a higher rank tensor. So this is M bar I j. So this is tensor of rank 2. Okay. How do I define that? This is Mij. This is a tensor in rectangular coordinates. This is the tensor in curvilinear coordinates. How do I get that? Once I have the transformation matrix, I simply have to T. So, Ij, right? So this has to be M. Let me write that as I prime. I prime, J prime, I prime. There are two quantities there, and then there is I, J. Is that visible?
Yes,
Should I zoom in?
it's visible.
Good. So that's the definition of a rank 2 tensor. If any, so the way it goes is that any quantity that transforms like this will be defined to be a tensor of rank 2. Right? So begin with the vector. In fact, you don't even begin with a vector, you start with a gradient operator because arbitrary vectors are hard to find. So start with a gradient operator, find your t, and once you have your t, any quantity that goes in multiples of t is a tensor. So that's a definite in general. So now I, j, so this could be higher. Any dimensional tensor is pretty much, the idea stays the same. J prime, prime, oops, I prime, j, and so on. Hopefully that's clear. And the best thing is to work with Minkowski space, where these things come out very nicely. Or rotation, yeah, actually, forget Minkowski. Rotation matrix is the easiest. Right? Or rotation transformation is the easiest thing. And one can discuss those things. Okay, that's all. Maybe I can tell you what I'm going to do next time so that you can maybe work a little. So I want to define what is a connection. Connection will be defined as the derivative of the basis vectors. So we define our covariant basis vectors. I will find the gradient of each one of them. So this becomes already, there was one vector, one index. Now there are two vector and one index if I talk in that language. So it's a dyadic with a one index. And curvature, now I should say that connection can be defined in many ways. Curvature, there is no unique curvature. So in a space, you can define more than one types of curvature. I will introduce what is called a Berry curvature. This is not the Ricci or Riemann curvature that we work with in general relativity. This is more, but ideas are the same. You can think of it as idea is the curvature, but different ways of defining them. And if I were to, so this will be del cross. I should actually, first of all, so that we find some quantity there. So this is the geometric structure. I should define this to be a dot. This becomes the components, and this will become connection. And then you build your curvature as del cross A. What is del cross del? What is del cross del of a function f?
Zero.
That's 0, correct? be
Yeah.
0. So for my, so there is this del cross. There's already a del there, but be careful. There is also this EI. So it's not, you have to distribute it. It's not obviously 0. Otherwise, it will be 0 all the time. Right? Notice there are second derivatives. I told you that curvature is second derivative, right? First derivative is the slope, second derivative is the curvature. So this is like the second derivative. So curvature always will have 2 derivatives. Any quantity that has 2 derivatives can be interpreted as some kind of curvature. That's a way to put it. So this is very curvature. That's all. Thank you.
On the left side of the board, it says derive.
This is what I meant where there was. So there is, let me write it here. So I can also ask what is a j in terms of a bar I. A bar I. Right. And there will be something else here, right? So this has to come on the other side. So it will be the inverse of P, right? So I called it S.
Okay.
Okay. And the question was to find SIJ. Just put in an attempt. Actually, this take it seriously because it's a very similar thing. You have to do this. I mean, I think I ask you to do it seriously because these are the questions I can ask in an exam. It's
Okay.
relatively small, and I expect that if I have done this, you should be able to do this. So it's more than an extra credit in that sense there. But I'll treat it as an extra credit, but take it more seriously. That's all.
All right. Thank you.
Thank you.
Mm-hmm. So Aliyah, your son will be learning all the curvilinear coordinates. You're muted, I think. You're muted.
Excuse me, can you repeat? I didn't hear you.
I said Aliyah's son will learn some curvilinear coordinates. Hello.
Yes.
Oh my god.
What did you learn?
Joking.
Hello.
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 They have a class and sometimes they don't understand something. I have to help them with computer.
Ah, nice.
Okay. Maybe I should stop.
Okay, bye guys.
Okay, thank you.
All right.
Bye.
Bye.
Bye, Jordan.